Okay, how many different ways are there to synthesize ethanol? Well, there's actually a few different pathways to synthesize ethanol. Ethanol is the active ingredient in hand sanitizer, so it was indispensable during COVID times. And we're going to look at some of the pathways that we can use to make ethanol today. In this lesson, we're going to look at types of organic reactions, part 2. And we're going to focus on esterification of alcohols and carboxylic acids, hydrolysis of esters, which is the reverse process of esterification. And we're going to look at transesterification, which is a technique that's used to make biodiesel. Okay, so esterification is a class of chemical reactions. It's a reaction between a hydroxyl group and a carboxyl group on adjacent molecules. And it's a type of condensation reaction. So esterification is one type of condensation reaction. And a condensation reaction is where two or more molecules combine and release a molecule, which is normally water. In esterification, one of the products that forms is an ester and the other product is water. So we have an ester that forms and the other is water. So let's have a look at an example. We've got our carboxylic acid with our carboxyl functional group. We've got our primary alcohol with our hydroxyl group. And what actually happens is these atoms become water and we break the bond here. So this carbon is here and we've got the rest of this molecule joined on here. Now, the ester contains the COOC atoms. So a COO group or COOC, COO from the carboxylic acid and the carbon from the alcohol. Two products are formed. The reaction conditions, we need concentrated sulfuric acid, so H2SO4 liquid, and heat, and it's an equilibrium reaction, so we've got equilibrium arrows. Now, to name the ester, we named the first part of the ester from the alcohol it was derived, and this was derived from propan-1-ol. So this section here is called the propyl part. So that's the propyl part. The carbon that's part of the ester group, the carbon that's got the double bond oxygen and then the single bond oxygen on the same carbon, that's one of the carbons from the carboxylic acid. So that's carbon 1. So we've got carbon 2. So this becomes ethanoate. So the name is propyl space ethanoate. We can write it in two ways. We can write it from left to right the way it's drawn as CH3COOC and then the rest of the molecule, so H2H2CH3. Or we can write the semi-structural formula from the opposite direction, which would be CH3CH2CH2OCO CH3. So we can write it in either of those ways. Okay, some examples. Esters have different odours and are really useful as flavourings. So depending on the combination of the acid and the alcohol, we get a range of distinctive odours or flavours. So, for example, butanoic acid, when it reacts with butan-1-ol, forms butyl, which comes from the butan-1-ol, butanoate, which comes from the carboxylic acid, and it's got the distinctive odour of pineapple. Ethanoic acid with ethanol produces ethyl from the ethanol, ethanoate from the carboxylic acid, and it smells quite different. It smells like nail polish remover, so not very pleasant. Heptanoic acid and ethanol produces ethyl heptanoate, and it tastes of apricot. Ethanoic acid and butan-1-ol produces butyl ethanoate, and it's got a characteristic flavour or odour of apple. And finally, ethyl butanoates derived from ethanol and butanoic acid. It's got a banana odour. Okay, let's look at a worked example. One of the characteristic flavours of pear is the compound butyl propanoate, which is an ester. Write a word equation for the synthesis of butyl propanoate from a carboxylic acid and an alcohol. So it says word equation. We know that we're producing butyl propanoate. This bit comes from the alcohol and the O8 comes from the carboxylic acid. Okay, so if we have a look, the carboxylic acid propanoate, that comes from propanoic acid. The butyl comes from butane-1-ol. They're always primary alcohols. The reaction conditions are sulfuric acid concentrated and heat, or we can use equilibrium arrows. That's also acceptable. And then the name of the compound comes from the alcohol derivative followed by the acid derivative. So it's butyl propanoate is the name of the ester. And the other product, of course, is water, because we're also forming water in this condensation esterification reaction. So writing a word equation including correct spelling of the reactant and the product names is a mark. So part B says, draw structural formulas for the reactants given in part A. So we know that we had propanoic acid and butane-1-ol, and the reaction conditions we've got concentrated sulfuric acid and heat. So if we have a look, we're going to lose a water molecule. So that becomes the water molecule as the second product. The carbon that's connected to the double bond oxygen is this carbon. And so this is carbon 1, 2, and 3. Carbon 1, 2, 3. That becomes part of the O8, the propanoate. And if we look, we've got our Cook group here. Then we've got 1, 2, 3, 4 carbons that were derived from the butane-1-ol. That becomes carbon 1, 2, 3, and 4 here. So this part of the chain is the butyl, comes from butane-1-ol, and the other part of the chain that I've drawn on the left here is the propanoate. So we've got structural formulas for the reactants and products, but that's done. And we've drawn an ester linkage, which I've actually circled here. You don't have to do that. But we also have the correct reaction conditions. So that's the second mark. Okay, classify the type of reaction shown in part B. It's called esterification, but condensation is also acceptable because it can be either of those. So that's the type of reaction, which is 1 mark. Condensation and hydrolysis of esters are reverse reactions. And we've already seen that we can have equilibrium arrows when we made our ester. So it makes sense that we could start off with an ester and react it with water, so the second reactant, to produce a carboxylic acid and an alcohol, which is the reverse of our esterification condensation equation. Now, in this case, water is a reactant that's used to break molecules. So we call this hydrolysis, not hydration that we talked about in the last lesson. So hydrolysis reactions are the reverse of esterification reactions. In this case, it's a chemical reaction in which water reacts with a larger molecule to break it into 2 or more smaller molecules. So water is a reactant. So we have 2 reactants here. Now, normally we produce 2 products, one which is an alcohol and the other which is a carboxylic acid. So let's start with our ester. The ester is named ethyl methanoate. Let's see where we get the name from. The carbon with the carbonyl group and the ester link is 1 carbon, so it must come from methanoic acid. And the other carbons, a part of the chain, come from ethanol. So we've drawn our methanoic acid. So we break our ester link, we break that, and we put the OH from the water. on to that carbon that's got the carbonyl group. So we've made a carboxyl group. So we've made methanoic acid here. And the other hydrogen from the water gets added onto the oxygen that remains and becomes hydroxyl group. So we have ethanol here. So ethyl methanoate reacts with water in the presence of acid, concentrated sulfuric acid and heat to produce methanoic acid and ethanol. Another really useful group of reactions are trans-esterification reactions, and they're very useful in making biodiesel. Biodiesel is a biofuel that can be synthesized from plant triglycerides or fats, oils that contain 3 ester groups. So they contain COOC groups. So here we have a triglyceride, and we've got a COOC, a COOC, and a COOC. So we have 3 ester links here. What we can do is we can react it with another alcohol. Normally methanol is used, but if methanol is used, then we're going to produce methyl esters. If ethanol is used, we will produce ethyl esters. So here we have 3 different molecules of methanol, and the hydroxyl groups are going to react with the ester groups to form 3 molecules of our methyl ester, which is our biodiesel. R means the rest of the molecule. R1, R2, R, R dash and R2 dash can all be different things, or they could be the same. And what actually happens is the backbone of the triglyceride, which is shown in blue, we end up putting 3 hydroxyl groups on that backbone, and that molecule is glycerol, which should be found in your data book or given to you in the stem of a question. So for one triglyceride molecule, we produce 3 molecules of methyl esters and 1 molecule of our glycerol. The reaction conditions that we need are hydroxide ions as a catalyst. Okay, so let's look at a worked example. Biodiesel is an alternative to standard petrodiesel fuel. Biodiesel is made from biological ingredients instead of petroleum, which is a fossil fuel. Biodiesel is usually made from plant oils or animal fats through a series of chemical reactions. In one process, a common triglyceride in palm oil, known as POP, is reacted with methanol in the presence of potassium hydroxide as a catalyst. The result is a mixture of methyl esters of the fatty acids, which are biodiesel molecules. What is the value of the stoichiometric ratio of the number of moles of methanol over the number of moles of POP? Well, we need 3 moles of methanol for every 1 mole of POP. So 3 over 1 equals 3. So our answer is 3. Okay, so bringing it all together, I suggest that you get some cue cards and you put individual reactions onto cue cards so that you can learn which reactants result in which products with the particular reaction conditions. But it is also useful to have a map like the one we've shown you here. You could actually transfer this onto A3 paper and put it up on your bathroom or bedroom wall so that you can memorise the reaction pathways. Right at the very start of this lesson, we talked about the different ways you could synthesise ethanol, which is a primary alcohol. We can do that via an alkene to a primary haloalkane to an alcohol. We can ferment glucose directly to alcohol. We've got all these different ways that we can produce. We've got an alkene that can directly, we can add or hydrate to produce an alcohol. So we've got lots of different pathways here. Okay, so we've learned a lot more in this second part of types of organic reactions. So esterification is a type of condensation reaction where we react a carboxylic acid with a carboxyl group and an alcohol with a hydroxyl group. In the presence of sulfuric acid concentrated and heat, we produce an ester and water. And the ester, the first part of the name is derived from the alcohol. We take off the ol and we replace it with il. The second part of the name is derived from the carboxylic acid. We take off the oic acid and we end with O8. Water is another product. In hydrolysis of esters, it's the reversed reaction of esterification. We start off with the ester. Water is a reactant. We use acid and heat as reaction conditions. We end up with a carboxylic acid and an alcohol. In transesterification, we start off with one triglyceride, for example, from plant or animal oils. We react it with 3 moles of methanol. In the presence of hydroxide ions, we produce 3 methyl esters, which are biodiesel, and 1 molecule of glycerol. Next lesson, we'll look at types of organic reactions, part 3. See you then. Bye.